Hey everyone, and welcome back to my science studio. In today's lesson, we'll be focusing on limiting and excess reagents, and I'll show you how to calculate the percent yield when you're given the actual yield from an experiment. Before we begin, make sure you download my free worksheet below in the description box so you can follow along and write down everything we do together. So without further ado, let's get to it. One way I like to explain limiting reagents to my own students is with a car example. And I want you to think about the chassis of a car, right? Which is basically the body or frame of a car. And each chassis needs 4 tires to make one complete car. So imagine you have one chassis, but now you have 7 tires. Can you build 2 cars? No, of course not. Even though you have plenty of tires, you only have one chassis, and so you are essentially limited to that one chassis. So you can only build one complete car. The extra tires, they just sit there unused. So in this scenario, again, the chassis is the limiting reagent, also called the limiting reactant. It's essentially the reactant that runs out first and determines how much product can be made theoretically. The tires are the excess reagent. You have more of them than you actually need. Specifically, since you started with 7 tires and you only need 4, then you only have 3 tires that are left over, right? They're in excess. And so, guys, in chemistry, the limiting reagent determines the theoretical amount of product that can be formed. The best way to understand these concepts is to actually walk through an example together. And here's the example problem. Suppose you have 5 moles of methane, or CH4, reacting with 12 moles of oxygen gas. And we want to determine several things here, including part C, which asks for how many grams of water will be obtained or produced. The first step you want to do is to always write and balance the chemical equation. So here we have methane, which undergoes a combustion reaction, which means that you have a hydrocarbon reacting with oxygen to produce carbon dioxide and water. So the unbalanced reaction is we have CH4 reacting with O2 to produce CO2 and H2O. Going ahead and balancing it, my trick for combustions is start with your carbons, then balance your hydrogens, and leave your oxygens for last. So for the carbons, we have 1 on each side, so we're good. Our hydrogens, we have 4 on the left and only 2 on the right. So if we put a 2 in front of the H2O on the right side, then 2 times 2, now we have 4 hydrogens on the right. Now counting our oxygens, we have 2 from the H2O and we have 2 from the CO2. So that makes 4 oxygens on the right side. And we only have 2 on the left. So if we put a 2 as a coefficient in front of the O2 on the left side, now we're balanced with our oxygens, and we have 4 on each side. Once our reaction is balanced, we can go ahead and start finding our limiting reagent. But here's the thing. We don't know whether the methane or the oxygen gas is the limiting. So we have to set up 2 stoichiometry calculations here. One starting with the amount of methane, in this case 5.00 moles, and the other starting with 12.0 moles of oxygen gas. And the idea is simple, you guys. Whichever reactant produces the smaller amount of product, in this case grams of H2O, is the limiting reagent. Starting with moles of methane, you can't get to grams of water in one step because you have one substance, right, your methane, and you're trying to get to a completely different substance, to water. And so when that happens, that should tell you that you're going to have to use a mole-to-mole ratio as a conversion factor somewhere here. And so that comes from the balanced reaction, right? The coefficients that you placed before we even started tackling this problem, right? In this given scenario, you're starting with moles of methane, so you can easily use a mole-to-mole ratio in the first step to go from moles of methane to moles of water. I say this because let's say if the question were to have given you grams of methane to start. You'd still use a mole to mole ratio here, but that wouldn't be the first step. The first step would actually be to go from grams of methane to moles of methane using molar mass. Because remember, anytime you want to go from grams to moles or moles to grams of the same substance, you use molar mass. I highly recommend you check out my last few lessons on how I tackle stoichiometry and conversion factors. I think they'll greatly help you in this lesson. But anyways, I digress. Now, I usually like to place a parentheses here and I draw a fraction. And I have to place the mole to mole ratio here as my conversion factor, right? So you go to the balanced chemical reaction, and I know that for every 1 mole of methane, you're going to produce 2 moles of water. We're going to place the 1 mole of methane at the bottom because you want to be able to cancel the moles of methane that the question stem gave you, right? So oftentimes I'll tell my students that if you ever get stuck, try to think about what you can put in the denominator of your fraction in order to cancel out your given units. So if the given unit is moles of methane, then the denominator should have the units moles of methane. And then the top should have the 2 moles of H2O. Now we have moles of H2O, we can easily go to grams of H2O by using the molar mass. Again, remember, anytime you have the same substance, right, in this case H2O, and you want to go from moles to grams or grams to moles, you can use molar mass. So going ahead and finding the molar mass, you end up getting about 18.015 grams of H2O per 1 mole of H2O. And you put the 1 mole of H2O at the bottom so you can cancel out the moles of H2O that you had from the previous step. So the last unit that hasn't been canceled is the grams of H2O, which is what we want, right? And if you're stuck on how I found the molar mass of water, I highly recommend you check back on one of my previous lessons where I talk about how to find the molar mass. You just use your periodic table. And so you take the molar mass of hydrogen and multiply it by 2 because there's 2 hydrogen atoms, and add that to the molar mass of oxygen on the periodic table. And you should get about 18.015. Now let's put all this into our calculator, right? So we have 5 times 2 times 18.015, and you end up getting about 180.15 grams of H2O. Now we're essentially going to do the same thing, only now starting with our 12 moles of O2. So we're going to open up a parentheses, we're going to draw a fraction, and then we're going to use the mole to mole ratio, only this time we need to find the ratio between O2 and H2O. So from our balanced formula, we know that for every 2 moles of O2 that react, we're going to produce 2 moles of H2O. Remember, only look at the coefficients here. Don't start going crazy and multiplying with the subscripts. The mole to mole ratio only comes from the coefficients, the numbers in the front of the molecules or compounds that you're dealing with. So we'll put the 2 moles of O2 at the bottom so that we can cancel out with the moles of O2 from our given value. And then we put the 2 moles of H2O at the top. Now that we have moles of H2O, we can go to grams of H2O using molar mass. So we know that for every 1 mole of H2O, we have 18.015 grams of H2O. So it's essentially the same step as last time. And when you multiply 12 times 2 over 2, which is just 1, times 18.015, you end up getting about 216.18 grams of H2O. And now comparing our results, we see that the reactant that produces the smaller amount of product is our methane. So our methane is the limiting reagent, and it produces a theoretical yield of 180.15 grams of water. Now, because our question stem gives us 2 values that each have 3 significant figures, our answer also has to be reported to 3 significant figures. It's always to the least number of significant figures. So looking at this 0, you look next door. Because it's below a 5, you keep it the same. So you leave it at 180, but you include the decimal point because without it, then this 0 wouldn't count. So having this decimal point here makes that zero count, and we have three significant figures. So what does this mean? Since our methane is the limiting, oxygen gas has to be our excess reagent. And if it is our excess, we really didn't need to start with 12 moles of oxygen gas. So how much should we really need? Well, we can solve that. So how many moles of O2 did we actually need in the experiment if we start with our limiting reagent, right? Our 5 moles of methane. We can go from moles of methane to moles of oxygen gas by using a mole to mole ratio. So going ahead, opening up a parentheses and drawing a fraction, we can say, okay, for every 1 mole of methane that reacts, we need 2 moles of oxygen gas. And again, I got this from my balanced chemical equation. So 5 times 2, that gives us 10. We needed 10.0 moles of oxygen gas. And again, I say 10.0 because we need to report with three significant figures. So how many moles of the excess reagent were then left unreacted, right? How many of our tires, right, were left unused? So you take the 12 moles that the question gave you to start, subtract it by the number of moles you actually needed, which was 10, and you end up getting 2 moles of oxygen gas left over. That's the excess reagent that remains unreacted. And lastly, before moving on to percent yield, this is a little bit of a trick question. It's actually part D, how much of the limiting reagent is left at the end of the reaction. If you're thinking 0 moles, then you're on the money. Why? Because, guys, remember, the limiting reagent is the part that runs out first. It's used up entirely in the experiment. You're not going to have anything left. But nonetheless, it's a question that gets some students tripped up, but not you guys, right? You came, you're watching this lesson, hopefully maybe you're taking notes, but if you're not, that's also totally okay. Just absorb as much as you can. Here to help you guys. But anyways, now let's go ahead and talk about percent yield because it connects directly to limiting reagent problems. And hopefully things will start making a little bit more sense here. So the formula for percent yield is actual yield divided by theoretical yield times 100. But what is theoretical yield? Well, the theoretical yield is the amount of product you should theoretically get in a perfect world. And I like to tell my students this. In a perfect world, I mean full of rainbows, butterflies, unicorns, you name it. This is the amount of product you should make. The theoretical yield assumes a couple things. One, that the reaction goes to 100% completion. Two, there are no side reactions happening. And three, you collect all of the product perfectly. But in real experiments, that rarely happens. You see, some common reasons for low percent yields include the reaction didn't fully complete, right? It went to 75%, 90%, 50%. Maybe product was lost during transfer, maybe when you were filtering it, decanting it, pouring it into another beaker. Some side reactions happened, right? So some cross contamination from the previous lab, maybe. Impure reactants, maybe the product was not fully dried. So these are some common reasons for getting a percent yield that's pretty low. And sometimes yields can even appear greater than 100%, which honestly totally violates the law of conservation of mass. But this usually means that maybe the product still contains some water or impurities, right? So if you didn't dehydrate it enough, there was still some water molecules attached, and that made the mass seem slightly heavier. Or maybe your measurements were just inaccurate altogether. I mean, there are so many reasons why you can have yields that are lower or higher, but ideally, we'd want a yield that's close to 100, right? And so, using our previous example, right, our previous calculations, we found the theoretical yield was 180 grams of water. But let's say in the lab you actually obtained 165 grams of water. How do you calculate the percent yield? All you do is you take your actual yield, which is 165, and divide it by your theoretical yield, which is 180, multiplied by 100, and you end up getting about 91.6666%. And if we were to round it to 3 sig figs, we end up getting 91.7%. And speaking from personal experience, if you obtained 91.7% of your desired product, I'd say you did a really good job. So kudos to you. And lastly, you guys, some final takeaways before we go is I want you to remember that the limiting reagent determines the theoretical yield, the amount of product that you should make in a perfect world, assuming that one, the reaction goes to 100% completion. Two, no side reactions occur along the way, right? So no cross contamination. And three, you have total product isolation at the end of your experiment. So that's the theoretical yield. And so if the question doesn't give you the theoretical yield, you have to find it by using the starting amount of the limiting reagent. In the event that they don't tell you which is the limiting reagent, so which of the two reactants, you have to do two separate conversions in order to figure out which one's the limiting, as we saw earlier on in this lesson. Remember that the actual yield is what you actually measured in the lab. And so to find the percent yield, you take this actual yield that you got in the experiment and you divide it by the theoretical yield, what you should have got in the experiment. And you multiply that value by 100, and that percent tells us how efficient the reaction was. And of course, our goal is to get a number that's pretty close to 100. Okay, you guys, that's all for today. Thank you guys so much for watching. If you found this lesson helpful at all, please like and subscribe. And don't forget to download my free worksheet in the description box below so you can practice these problems on your own. I'll see you next time in my science studio, but until then, happy studying.